Earthquakes are among the deadliest of natural disasters, with 60% of all deaths from natural disasters being linked to earthquakes. In the 20th century alone, about 1.7 million deaths were attributed to seismic activity. The major reason earthquakes are so deadly is that they cause structures to collapse, sometimes violently and without warning. This could be resolved by using a material with greater tensile strength and adequate ductility, but such a material is typically more expensive. So, there is a need for a cost-effective material which has a higher ductility and tensile strength. ECC, Engineered Cementitious Composites, also known as bendable concrete and initially developed by Victor Lee in the 90s, is a novel material having excellent inherent ductility and improved tensile strength. ECC constituents are similar to those of conventional concrete, but with the absence of coarse aggregate and the addition of fibers. ECC exhibits strain hardening under uni-axial tension, which allows this material to bend and form multiple cracks over the entire surface instead of a single localized crack that could spell disaster. The development of composites dates back to the 1990s, but surprisingly, despite their numerous benefits, we don't see many ECC structures around us. There are certain restrictions which limit the commercialization of ECC, mainly, number 1, complex material designing process and its unknown characterization and performance under real loading. Material designing of ECC is quite complex and based on extensive experimentation. The major concern is to find out the critical volume fraction of fiber for any particular matrix. Critical volume fraction is the minimum volume of fibers needed to ensure strain hardening behavior. Different researchers have come up with different approaches to find this critical volume fraction. These include a composite mechanics approach, a debonding fracture energy approach, and a micromechanics of crack bridging and fracture approach. These models provide simplified equations for finding the critical volume fraction, but the variables involved in these equations are needed to be found experimentally. For example, in the model based on micromechanics, we need to find the complementary energy of matrix fiber, a frictional bond, and snubbing coefficient, which makes this process quite lengthy, time-consuming, and uneconomical. The solution is to implement machine learning for material designing. For this purpose, a total of 435 data points were collected to train a machine learning model, which included both FRC and ECC, to make the model familiar with two different types of post-cracking behavior. The working of the model is quite simple. It will ask for mix ratios and fiber properties and will predict mechanical properties and fracture behavior of the resulting mix. Fracture behavior means whether the mix will give strain hardening or strain softening in tension. An accuracy of 98% was achieved using this model. In this way, even a layman can easily design a mix without any experimentation. The second problem is to study the behavior of ECC at the structural scale. ECC possesses an excellent post-cracking response with increased capacity. Its behavior on material and member level has been widely studied using sophisticated FEA, but its structural response has not yet been confirmed. In our project, structural designing and performance-based evaluation of ECC structure was conducted considering a realistic types of loading incorporating dead, live, and seismic loads. The comparison between ECC and RCC is carried out to get the comparative idea of its design and seismic response. Total 3 models developed for comparison. These are RCC with adequate cross-section, ECC with adequate cross-section, ECC with same cross-section as that of RCC. The design actions calculated using linear static analysis were quite less for ECC reduced cross-section model due to lower unit weight of ECC, which leads to less self-weight and lower inertial forces to develop within the structure. For designing, ACI 318 was used for RCC while JSCE guidelines were used for ECC, using the design actions calculated from linear static analysis. The result showed up to 25% reduction in the cross-section and about a 30% reduction in steel requirement that cut out the total structural cost of 11.7%. An ECC is a novel material having a higher amount of ductility. Therefore, a non-linear analysis should be conducted to determine its actual seismic response. Also, GSCE guidelines for designing have no legal standing. Therefore, performance-based evaluation is performed to eliminate any uncertainty. For this purpose, pushover analysis and nonlinear time history were performed, which demonstrated that damages in the ECC structure were considerably lower as compared to RCC. The study concludes that irrespective of the addition per unit cost of ECC, on a structural scale, ECC is a cost-effective material with superb seismic performance. In conclusion, these two studies are tiny steps towards the commercial implementation of ECC on a structural level. Using these studies, one can easily design the mix of ECC first and then proceed towards the structural designing, following the ISMD approach proposed by Lee. Once deployed at scale, this beneficial material will save lives every day. Bendable but not beatable, ECC is the concrete we needed yesterday.